Hey, it's Dr. B here. Let's do some atomic bookkeeping. For a given atom, let's keep track of the number of protons, which carry a positive charge, the number of neutrons, which are also in the nucleus, and they vary from sample to sample, from atom to atom, and they carry no charge. And let's also keep track of the number of electrons, where electrons are given a negative charge. The atomic number simply means the number of protons. On most periodic tables, it's the blue number. It's the only part of an atom of these three subatomic particles which does not vary. For example, if it's hydrogen, it has to have one proton. Helium has to have two. And sometimes they put the number right there. That's the atomic number. This cannot be. If it's sulfur, it must have 16 protons. If it was 32, it would be a different element. The mass number also adds the number of neutrons. Therefore, the mass number is equal to the number of protons and the number of neutrons. I've written this way so you can take notes as efficiently as possible. And if you think about it, that means that to come up with the number of neutrons, you have to do a little math. So they usually write it like this. This is at least the old-fashioned way of writing it. This is helium-5. I mean, this 2 is there, but if you think about it, the number 2 can never vary. Helium always has 2. It also shows that the number of neutrons in helium-5 is 3, 5 minus 2. It's a little quicker just to write it like this. This is a dash, not a negative sign. And this is the isotope known as helium-5. It's the same thing as this, and as we've said, it must have 2 protons, otherwise it's not helium. The rest are neutrons, and there's 3 of them. This brings us to the topic of what is an isotope. I think that there's really 2 meanings of the word isotope. People use it in common language when they're referring to an atom that has a single atom, right? If they refer to an atom such as this one, we call this the helium-5 isotope, that particular variant of helium that has 3 neutrons. It's also used for comparative numbers, right? It's those 2 different atoms where the number of neutrons varies. Example, helium-4 and helium-5 are isotopes. They vary in the number of neutrons. But in common language, you'd also say, which isotope? Oh, helium-4. Which isotope at another time? Oh, helium-5. So really, I see 2 meanings there. An ion similarly has 2 meanings. It's a case where you don't have the same number of protons as electrons. Now, protons never get removed from the nucleus under chemical situations, so the electrons are being removed. That happens very easily and predictably. It can go 2 ways. You can either have more electrons or less electrons than protons. And if it's a positive charge, well, you must be more P than E, right? More positive than negative. Since sodium must have 11 protons, the number of electrons in the sodium ion, which is positive, is 10. We'd call that a cation. The number of protons is greater than the number of electrons. Ca plus ion, if you think the T is a plus. Or cats have paws, and paws are positive, if you like that one. That usually gets a laugh. If you're in the situation where you have an ion that has 20 protons and 18 electrons, well, that's a +2 ion, isn't it? And since 20 must be calcium, this is the calcium dication. Please don't pronounce it as dication. I see that sometimes. If you have a negative ion, well, then the number of E's is greater than the number of P's. We call that an anion, a negative ion, anion. And say you have 7 protons and 10 electrons, well, that's a -3 ion, is it not? And it must be nitrogen, since only nitrogen has 7 protons. This is the nitrogen trianion. Since isotopes are evident throughout the periodic table for each element, that means anytime you have a pile of those atoms, they're going to have different masses, even carbon, even hydrogen. If you have a pile of carbon atoms, the mass has to be a weighted average of those isotopes. So we need an average. On a periodic table, it's typically the red number. And this usually works out extremely precisely, since even for a very small sample of atoms, you have a very large number of atoms. And here's the case for carbon. 98.9% of carbon atoms are carbon-12, that variant, which has 6 protons, in addition to the 6 protons and 6 neutrons. But if you have carbon-13, you have one extra neutron, and that's the rest of the sample, only 1.1%. So you can see that the average atomic mass is going to be very close to 12 atomic mass units. And to take a weighted average, just simply multiply the abundance times its mass, and then sum them up. 98.9% of it is 12, and that's almost all of it. So we'll change that to an abundance, 0.989. Move it 2 decimal places to the left. And the rest, or 0.011 as an abundance, is atomic mass 13, not a big contributor, and therefore we have a very close average atomic mass to 12. Don't write the abundance as 0.11, that would be 11%. I see that sometimes. Always move it 2 decimal places to the left. Another useful concept is the band of stability. It has been observed, and we won't go into the details why here, that if you have more than 1.5 times as many neutrons as protons, it's just too many and the atom is likely to decompose. Or to put it another way, if the number of neutrons divided by the number of protons is greater than 1.5, you've got an overcrowded house and things are going to fall apart. Let's try it for uranium-238. Well, 92 of the units in that mass number came from the protons. The rest must be neutrons. I get 146. Do the math. Neutrons divided protons. Yes, we are above 1.5. Run away. That thing is radioactive, giving off gamma rays, very dangerous. Finally, I'd like to introduce a term known as isoelectronic. And fluorine anions and neon are examples of that. They both, if you think about it, have 10 electrons, right? Neon, 10 protons, 10 electrons. Atoms always have the same number of protons as electrons. Fluorine is not an atom, it's an ion. Note that distinction. That shows up on tests frequently. Is fluorine with a negative charge an atom? You might say to yourself, of course it's an atom, but it's an atom that has an extra electron, and therefore we call it an ion. That seems right, but that's not how you'll see it defined. They draw a big line between an atom and an ion. Once you change the number of electrons, you are no longer an atom, you are now only an ion. And in this case, you've got your 10 electrons because 9 plus 1 is 10, because the negative charge, more E than P. And therefore they are isoelectronic. Now that term might not seem to be that significant, but oh boy is it, because that is the key to all chemical behavior, is that all atoms seem to want to be like noble gases. Neon is a noble gas. Fluorine will always gain an electron to become like a noble gas. That's a little insight into chemical behavior. Okay, that's atomic bookkeeping.